Hello, today I'm going to talk about general relativity, a theory developed by Albert Einstein in 19th century. So this theory tells us how the universe and the different objects of the universe like different star systems, black holes, planets work in the universe. So general relativity was created in order to better understand gravity. It has helped us to answer why gravity exists. General relativity has many predictions, most of which have been verified by experiment with amazing accuracy. So the predictions of general relativity, one of them is what will be the fate of our solar system, what is the fate of our sun, what is the fate of our galaxy. So it has many different predictions that scientists are deriving and predicting, and these different predictions have been verified by experiments. So general relativity has three different relativistic concepts like time relativity, mass relativity, and length relativity. So one of the interesting relativity concept is the time. So the special theory of relativity encompasses inertial frames of reference moving at uniform relative velocities. So Einstein asked whether or not systems moving in non-uniform motion with respect to one another could be relative, and came up with the idea of general relativity. So one of the time relativistic equation is this one, which is del t prime equals del t divided by 1 minus root over 1 minus v square by c square. So del t prime is the time of the moving object, accelerating object around another object. So this object is stationary with respect to the moving object. So if we describe the time of the stationary object as del t, and the time of the accelerating object as del t prime, the relational equation will be described as this equation, so which expresses the fact that moving observer's period of the clock is longer than the period in the frame of the clock itself. So the beginnings of general relativity germinated in 1907 with Einstein's thought experiment concerning a free-falling observer that he called the happiest thought of his life. So which is a free-falling object? We all know that a free-falling object wouldn't have any gravitational field. So for an observer falling freely from the roof of a house, the gravitational field doesn't exist. And also suppose a vehicle is accelerating at a rapid speed, wouldn't feel any gravitational field around it. If it is moving at a speed of light, I don't think there will be any gravitational effect. It might bend around, it might have like a slightly bent around an object, but it didn't feel any gravitational field when moving at that speed itself. So by 1915, Einstein had developed what are known as the Einstein field equations. So Einstein field equations is this one, which is G mu v, which is Einstein's gravitational constant, which is the Einstein tensor. So this one will be equal to 8 pi g, which is g is the Newton's gravitational constant, divided by c to the power 4. C here is the speed of light, times t mu v, which is the stress energy tensor. So it describes that how the gravitational field will be affected when there is a presence of a massive object in the universe. So the massive object's gravitational field, which is described as this Einstein tensor, and will be and the relation between Einstein's gravity and the Newton's gravitational constant can be described with these equations. So GR also is a theory of gravitation that supersedes Newton's law of universal gravitation, using warping of space-time by mass to explain gravitational attraction instead of the idea of forces. Essentially, massive bodies warp and curve their local space-time. The stronger the gravity, the more space-time is warped. Light is deflected from its original straight path when traveling traveling through a massive object. So if the light is traveling around through a straight path, and there is a big object which is a very high gravitational pull, or the space-time is bent around it, the travel of the light path will be bent around it as well, which is a very interesting idea that we all know this light is travel around a straight line through its path, but actually through experiment it has been seen that light actually bent around a massive object, even around the sun. So general relativity tells that light travels along the curved space. So if there is a massive object, it curved space-time around it, and the light travels along the curved space, taking the shortest path between 2 points. So if the light is traveling from point here to point there, and the light is deflected toward a massive object, the stronger the local gravity, the greater the light path is bent. So if the gravitational pull is very high, suppose a black hole is present on here, the light will be bented at much higher than if there is if suppose we have if there is a planet here, the light path will be less bent in that case. So the higher the gravity, or the higher the space-time is curved, warped around it, the light path deflection will be higher. So another concept is called geodetic deviation, arises from the transportation of angular momentum through gravitational field when energy field equations are applied to a massive body. So massive bodies like Earth warp space-time, and the spinning object orbiting the larger body will exhibit a processing of its axis of rotation. So rotating massive bodies pull space-time around with them. So gravitational lensing effect occurs when light reaching an observer has passed by a very massive body which is heavily distorting space. The light can be seen to bend around the body, as I have already said. Another concept of general relativity is black holes. We already found black holes during different experiments and observations, which is a profound prediction of general relativity. A black hole is a large body of matter that is so dense that nothing can escape its gravitational attraction at a given distance, known as Schwarzschild radius. So the radius beyond the radius that around which the area that it creates by a black hole, and within that radius nothing can escape, not even a speed of not even a light can escape that radius. So that radius is depicted with an equation which is Schwarzschild radius Rs equals 2 times g times m, which is g is the gravitational constant, times the mass of the black hole divided by c square, the time speed of light square. So the radius can be calculated of that Schwarzschild radius, within that radius that nothing can escape. not even a Earth. If it is traveling toward the black hole, not even a speed, not even a light, or not even any object or a spaceship, it cannot escape the black hole, that Schwarzschild radius. So gravitational waves, what is gravitational waves? It's a fluctuation of space-time curvature that is propagated as a wave. So if there is an object, like suppose Earth, it will create a curvature of space-time around it. And suppose there is we have a sun. We have a sun, or like we have only one sun in our galaxy or in our solar system. But if in the future we might find that we have lots of stars like our sun in the different galaxies. So each of the massive object will create a fluctuation of space-time curvature, and this fluctuation of space-time curvature is propagated as a wave, and this wave radiates away from accelerating bodies. So if all planet system or all star system is accelerating relative to one another, so this and they create a space-time curvature, and this space-time curvature is propagated as a wave, and it radiates away from their respective bodies, and this carries energy away from the source. And these gravitational waves predict that two massive bodies rotating about the center of mass will lose energy in the form of gravity waves, and the orbit will decay. So suppose these two moving objects has an orbit. So when their space-time curvature or the gravitational waves decay, it will the orbits will decay, and eventually it will merge to the center of the object to the center of the object, which is suppose a black hole, and the rotating objects will merge towards it, because this object has a massive gravitational wave, and it has a space-time curvature created by it is much higher than the other two objects that are rotating around it. So this is the mainly this is the main concept of the general relativity, and how it affects moving objects, and how the gravitational waves created by different objects plays a role in the universe. Thank you for listening. Thank you.